All right. I have to tell you guys, you are my fun class. It's nice to chime in. You know, I'm running a little late here every time I come into class because I come out of my office hour, and I turn on the Zoom meeting, and there's already 10 of you, 11 of you already here, and that's a high percentage of the class compared to my calculus students. Can I just say they are obviously very tired of the semester, and they're starting to drop off. So congratulations and thank you to you guys who are participating. All right, do you have any comments or questions for me before we get started on anything else? So I'll tell you, we have 1, 2, 3, 4, 5 more class days, including today. That's it. So we're just going to finish out this week, and next week is our last. So today will be the last day that I'm going to be doing these discussions about so many powers, but I have a few things in store for you there. And then next week, when I spoke to you guys, I guess it was last Tuesday, about how things are going, I got a few interesting suggestions about what we can do with the remaining time in the class. And I think I have some topics that will appeal, that sort of overlap between a couple of the suggestions that I heard. So we'll be switching to something different after today. I'll save it as a surprise for starting on Friday. So knowing that today is going to be your last day to talk about these power residues, do you have questions about that topic? Oh, let's see, somebody in the chat here. It's hard to read sometimes. That's a good point. You're having trouble reading the stuff that I write on the slides. I said I was going to switch to marker, and I have not. I went backwards, didn't I? I'll try to use marker today and see if that'll help. But I can't scan the previous days because I don't know if I saved the stuff that I wrote. So Elena, I don't know, are you hoping that other people will share their notes? But I'm sure she's, oh no, yeah, she's still here. Well, if you, maybe Elena, bring this question to me later, and we can try to figure out what it is that you need, and I'll try to make sure you have what you need to understand the material. All right, so I want to actually do some computations today that use some of these primitive roots and show you the kinds of tasks that we can solve and the things that we can discover just from having the existence of a primitive root. So let's slide this one in. All right. All right, so let's first do some calculations to make sure we have a primitive root. I'll take a reasonably small prime number modulus. We know if we have a prime modulus, then for sure there must exist a primitive root. So let's use our modulus to be just a 7. And then I can look for what the possible primitive roots are. You know, you have to use an invertible congruence class modulo n. So there's 6 of those. It's never 1 nor -1 because the order of 1 is always 1, and the order of -1 is always 2. Then it's just a question of looking at these, but we notice that 2 is a number of too low in order. 2 cubed is equal to 1. But that sort of forces it to be true that if you look at 5 cubed, well, 5 cubed will be the same as minus 2 cubed, which is the negative of 2 cubed. So since 2 cubed is already a 1, this is already a minus 1. So raising to the third power doesn't get me to a 1. Raising to the second power obviously doesn't get me to a 1 either. So the smallest exponent that will work will have to be, well, 5 cubed squared is 1. So here's an example of a primitive root. So I will use r equals 5 as my primitive root. All right. And by the way, you saw that I decided that it was a primitive root, not quite by using the definition of a primitive root. I did not yet go through all of the powers of 5 to see when I got back to 1. I just phrased it in terms of the order of the element. What's the smallest exponent that does work? We know that the order is always a divisor of phi of n. It's a divisor of p minus 1, which would be 6. So if the order isn't 1, and the order isn't 2, and the order isn't 3, then the only thing left is that the order has to be 6, and that makes it a primitive root. But now let me actually use the fact that, use the very definition of being a primitive root, and I know now that I won't get any repeating residues mod 7 until I've gone all the way to the 6th power of 5. So here they are. 5 to the 0 is obviously congruent to 1. 5 to the first is 5. 5 second is 25. Mod 7 is a 4. 5 cubed is 5 times the previous one. So, or actually I already did this one, so that was the 6. 5 to the fourth is the square of 5 squared. So 16 is congruent to 2, modulo 7. And 5 to the fifth has to be what's ever left, which is 3, because 5 to the sixth we know is going to be congruent to 1, and then the pattern will repeat. So here you see all of the non-zero residues, the invertible residues, mod 7, but I've lined them up according to the exponent of 5 that appears. Most people would not go through the trouble of writing the little triple bars, and you don't have to keep writing all of the 5s all the time. Instead, let's see if I can get a better marker. Instead, you just kind of write this as a table. 0 corresponds to 1. That's too thin. Doggone it. I have many markers, and they never seem to. 1 goes, there we go. 1 goes to 5, 2 to 4, 3 to 6, 4 to 2, and 5 to 3. Okay, so what is the process, that connects these two rows? If you call the elements in this row x, thinking of those as the inputs, then the outputs are 5 to the x, or more precisely 5 to the x reduced mod 7. It's the congruence class of 5 to the x mod 7. Well, come on, you guys had this in high school. You know, when you have a table of values of x's and y's, you're thinking about this as being a function. These are the inputs, these are the outputs. You could make the graph. Okay, the graph doesn't look like much. If you try to show the graph on Cartesian coordinates, you would just see the y coordinates hopping all around with respect compared to the x coordinates. You can sort of show the graph on a spiral if you think about this as being a function. I can show the graph. No, let's do it this way. The graph of any function is the set of pairs of inputs and outputs where x ranges over the domain. That's what the graph of a function always means. And in our case, the inputs were integers, but I can think of those as being part of the real numbers. The outputs, on the other hand, those are congruence classes mod 7, so I can think of those as being parts of the real numbers modulo multiples of 7. And by that I mean, take all the numbers from 0 up to 7 and simply glue the two edges together. Or to say it another way, you take the whole real number line and you declare two real numbers to be equivalent if they differ by a multiple of 7. That's the same definition that we give for our congruence classes. Two integers are congruent if they differ by a multiple of 7. But now I'll declare two real numbers to be equivalent if they differ by, well, 7 or 14 or whatever. So these two numbers will be declared equivalent. And these two numbers here that are about, I don't know, 50 or 60% of the way through, they'll be equivalent. So you end up with these equivalence classes. The easiest way to visualize this equivalence relation is to take the real number line and make it spiral in a kind of a corkscrew shape. Where if the number 0 is right here, I want you to wrap it around so that the number that's directly underneath the 0 is the number 7. And then likewise directly under that will be the number 14 and so on. So when I said that these two numbers were equivalent, well, one of them was here between 0 and 7, and the other one was between 7 and 14, and it lies directly underneath. So we're making our equivalence classes by just looking to see which ones of these things lie above each other. And if you now stand way at the top of this picture and look straight down, all you will see will be a circle, where I guess the way I've written it is kind of backwards from the way people usually do it, but I'm looking down at the number 0 being here, and then the rest of the interval from 0 to 7 is spread around the circle just once. So I'll get 1, 2, and 3 on this side, 4, 5, and 6 on that side, and these are at the corners of a regular heptagon. So this process of creating numbers mod 7, if you just look at it as saying, well, where do things lie in among the integers from 1 through 6 inclusive, you don't get any interesting part of the graph. But if you think about it as being taking place on this spring, then the graph is actually pretty easy to understand. This is where the outputs lie. These are where your y-coordinates are going to be. They're integers mod 7, but that means that they're these congruence classes. You're talking to me about which one of the stacks you're in. On the other hand, the inputs are just, well, integers, but that's part of the real number line, which from the way I'm drawing this picture, and I really am hunting for some darker markers. It's working now. Yeah, that looks better. I will pair off the integers here. Let's start off with, I'll put 0 there, and then 1, and then 2. And so on. Every integer gets paired off with its congruence class on the spring. So here's 5 to the 0 power, meaning the real number 5 to the 0 power, that's 1. And then 5 to the first power is 5, so that gets sent here. And 5 to the second power gets sent to 25, so that's almost 2 revolutions around this picture. So here's 25. And so this function that we're setting up, it's kind of got the ordinary exponential function wrapped into it. You're taking the integer inputs between, let's say, 0 and 6, or 0 and 5 inclusive, and you're finding out the real numbers that you get by taking 5 to that exponent. Those will be somewhere on the real number line. They're obviously going to be spaced kind of exponentially apart. I guess I don't have to tell you guys what the graph of this would look like in a calculus class, what that graph would look like. But once it's embedded on the vertical axis, you twist the vertical axis up into the spiral and project down to get these congruence classes mod 7. So what's the upshot of all this? Well, you feel like you understand the exponential function very well as a function from the reals to the reals, and you can see the information is still embedded in this coil, but now when you project downwards, it feels very erratic how exactly you bop around on the circle. This was 5 to the 0 power was 1, and then 5 to the first power jumped all the way over to 5, and then next we went to 5 to the second power, and 5 to the third power, 5 to the fourth power, 5 to the fifth power, and then finally 5 to the sixth power was back to being 1. So when you're only presented with this table of values, it feels very erratic. It feels like this is something, well, cryptic, which is how this technique gets involved in cryptography. All right, so keep that in mind, that there is, it's not just a random display of integers. It's obviously calculated according to a well-defined pattern, but that pattern looks very difficult to disentangle when you only work with the congruence classes mod 7. Now, what do we do with all this kind of stuff? Well, one of the things that we do is we try to be like high school students. Once you have given the graph of y equals 5 to the x, then you study from this graph, you observe that this is an increasing function, and in particular that means it's a one-to-one function, which means that it has an inverse function. If you flip the x and y coordinates around, then you get a graph like this. And you guys know what the function is that you're graphing now. This is a new function. It's called the logarithm base 5. It's only defined for positive numbers, but that's fine. Well, we have the same phenomenon happening here. The fact that 5 was a primitive root meant that you would not get any repetition. You would not ever come back to a 1 until you had gotten past this point on the table, this table of values. So that meant that all the numbers in the second row were distinct, which is to say that this function is now one-to-one. And if you have a one-to-one function, you can flip the x and y axes around to get the inverse of that function. So if I do that, can I write this table in the vertical format that's more familiar in high school? The inputs go like this. The inputs to this new function will be the outputs from the previous one, and that turns out to be all of the invertible congruence classes mod n, again. But the exponents are not. Those exponents will include 0. Sorry, the outputs from this function will be what used to be the inputs, and that did include 0. In fact, it's not even really a good idea to think of these things as congruence classes at all. If anything, they are congruence classes modulo 6, not 7. And, well, when I figure out what were the x coordinates that used to go with the y coordinates, those will now be the y coordinates that go with the x coordinates, and I can make the table of values like this. Let's see, 2 corresponded to 4. An output of 3 came from an input of 5, so now 3 is the input, 5 is the output. 4 corresponds to 2, 5 corresponds to 1, and 6 corresponds to 3. And I don't know why I put the 7, because nothing corresponds to 7. But since you're working mod 7, these are elements of the integers mod 7. 7 is the same as 0, and well, you don't get 0 by exponentiating anything. That's why there's no dot on this vertical line in your high school graph. All right, if you follow the pattern of what you did with your high school functions and you see what I did here, then it seems perfectly reasonable to describe this function. It's a well-defined function now, and you could call it the logarithm base 5 of the number x. You could, except that for historical reasons, nobody ever does. Instead, it's called the index mod 5 of the number x. But it will have the same features as the logarithm, it will be the inverse function to the exponentiation function that I had over here. It will be a well-defined function on all of the invertible congruence classes mod n. On the non-invertible congruence classes, this function is not well-defined. There's no exponent that you can put on your primitive root to get a non-invertible congruence class. All right, so that's the basics of how this index function is defined. I want you to think of it as just being the same as a logarithm, except it's all with modular arithmetic. I will say too, since we got all of our values for the invertible congruence classes mod 7 by just taking an input between 0 and 5, I'm only putting the outputs between 0 and 5. But you can think about these outputs from this index function as being elements of the integers modulo 6. Rather than thinking of them as just small integers, think about them as being integers modulo 6. That, in other words, here you could be saying that the index of 4 is not just 2, but it's 2 or 8 or 14 and so on. And the rationale for that is that if you do take 5 to the 8th power or 5 to the 14th power, they will be congruent to just 5 to the 2nd power. The reason, of course, is by Euler's theorem, since 14 is 2 6s with 2 left over, from your laws of exponents, this will just be 1 squared times 5 squared. So I will, in a few minutes, I'll need to get used to thinking of the index as being that way. I will always write an integer between 0 and 5 inclusive, but the index is really an element of this set of congruence classes. So, how does this function behave? Does it behave something like the logarithm function? Well, I don't know. What features of the log function do you remember? So let's have these as a collection of theorems. And I will say it this way. If R is a primitive root mod n, well, so first of all, that's going to imply that n is a number that has a primitive root. And as we've been discussing for the last couple of days, that means that n has got to be a power of just a single odd prime, or maybe twice an odd prime, or the number 4. But in those even cases are really not very interesting. So I'll just assume n is the power of an odd prime. Then this index function is well defined on all of the invertible congruence classes mod n. And let's list a few of its features. What can you say about the index mod r of the number 1? Well, the index mod r of the number 1 it's the number that you have to exponentiate to get a 1, and of course that's a 0. So just as the log of 1 is equal to 0, you have this property. Second, what can you tell me about the index? This is the key one here. What can you tell me about the index of a product? So if A and B are both invertible congruence classes mod n, then so is their product. In fact, the inverse of the product is the product of the inverses. What do you get as the index of A times B? Well, you get the same as the formula for logarithms. It's the index of A plus the index of B. And the proof of this is easy. I'm asking you what exponent you could use on this primitive root to get A times B. And the answer is, well, if you already know that r to the, let's call it x, gives A, and r to the y gives B, if I call this number x and I call this number y, then what you're saying is that r to the x is equal to A, and r to the y is equal to B. And so if you multiply together x plus y powers of r, the first x of them will give you an A, and the remaining y of them will give you a B. So that means that this is exactly the index we're talking about. With the understanding that I'm going to be working in the integers modulo phi of n. So if you would like, I can say that these two will be congruent to each other modulo phi of n. Or they are the same, this left and right side are the same element if you look at the congruence classes of z modulo phi of n. So just take an example in here. If I wanted to multiply 2 times 3 to get 6, I should be able to add the indices of 2 and 3 separately. Well, 2 and 3, I mean, the indices of 2 and 3 are 4 and 5. Their sum is 9. I didn't get a 3, but I did get something that was congruent to 3 modulo phi of 7. It's congruent modulo 6. So that's giving me an answer that's congruent to what I started with. If you combine these two results, then you get the following. It says that the index mod R of the multiplicative inverse of A is just the negative of the index mod R of A. Because A and A inverse are two congruence classes mod n that multiply out to be congruent to 1. And so the index of their product is the index of 1, which is 0, but the index of their product is the sum of their two indices, so they have to be negatives of each other. And as usual, this just means they're actually congruent. Those two expressions are congruent to each other modulo phi of n. Another one that comes from iterating statement number 2 is another property that you remember from your logarithm days. In fact, this, you can think of this one as a special example, although I have it in mind that the n that I'm about to write down is a positive integer. The index of a to the n is just going to be n times the index of a. So this result, for positive numbers n, this result follows by induction from this result. Obviously, if b were equal to a, you'd have the index of a squared is twice the index of a. And now use the statement again where b stands for a squared. Now the index of a cubed is the index of a plus the index of a squared, which we have already proven to be twice the index of a. So that's 3 times the index of a. So the proof of this one for positive n follows by induction. And if n is a negative integer, you can combine that previous step of number 4 together with number 3. So you start to get a lot of descriptions of how you can work problems with indices. You can even handle the case where you want to sort of change the base. Do you remember this formula? If you wanted to look at, for example, the natural log, no, let's do it this way. If you wanted to get the log base a of a number b, you could write it as the natural log of b divided by the natural log of a, where natural log really just means log base e, and your teachers may not have mentioned it, but in fact the e doesn't have to be e, it can be any other base. So this is a way of computing logarithms to different bases. Well, we have a similar thing that we can say here. So I'll put that in as step number 5. If s is also a primitive root, then the index mod s of a number, well, I'll do it, you know, I'll use b, is equal to the index in, mod r of the same number b, divided by the index mod r of this new base s. And before you object that indices are supposed to be whole numbers and this looks like a fraction, let me just assure you right away that what I really mean by this, I'm sure you can guess actually, is that I want you to take the index of B mod R and multiply it by the index mod R of S. And this is congruent, like all of our other statements about the index, this is going to be congruent modulo phi of n. Well, that actually poses a little bit of a problem. You should be asking, how do you know that this element of z mod phi of n actually has an inverse? So if I go back to the one example that I did earlier, where I was working mod 7, then phi of 7 is equal to 6, and there's a lot of things that don't have an inverse mod 6. In fact, the only things that have inverses mod 6 are 1 and negative 1. Those are the only two elements of z mod 6 that have inverses, which makes it sound like, gee, this index mod 5, I was using 5 before, the index mod 5 of this other primitive root can only be 1 or negative 1. Oh, well, who has an index of 1 or negative 1? The thing that has an index of 1, of course, is the primitive root r that we had earlier. I don't see negative 1 on this table, but of course we're working modulo 6, so negative 1 is the same as a 5. And so apparently the other primitive root, the only other primitive root I could have used was 3. So it sounds like the only example that I can point you to for this particular instance, when n is equal to 7, if you're already using r equals 5, then your s has to be 3. And then the rest of this is true. This 3 is the inverse of 5. So if you ask me what exponent you need to put on 3 to get a number b, I would say, well, let's just take the negative of the index that you used, of the exponent that you used on a 5. But that's exactly what this formula here says. The index of mod 5 of the number 3, that's the negative 1, because 3 is 5 to the negative 1 power. 3 is the inverse of 5. So dividing this index by a negative 1 just means taking the negative of that index. All right, once you've worked through exactly what it is that this is trying to say, and again, I want to emphasize the connection to logarithms, it's actually pretty easy to prove. It's got a little more details than the other ones, so let me write this proof out. So first note that the index mod r of s is invertible modulo phi of n. And the reason why is the fact that r is a primitive root says that all the invertible congruence classes, mod n can be written as a power of r. So let's do that. When you tell me that s is another primitive root, then at the very least you're telling me that x is invertible. So s must be expressible as r to the, let's say, k power for some integer k. And then this number k, that's this index. So why do I think that that's an invertible element modulo phi of n if the GCD of k and phi of n is some number d that's more than 1, then let's see, r to the something will be, let's see, how do I want to do this? Oh, yeah, let's write, I've done this many times with you guys now. Whenever I'm playing around with these exponents and I'm looking at this GCD, I keep using the Bézout theorem. It makes the calculations go so fast. You write the GCD as being a multiple of k plus another multiple of phi of n. And then when you take s to the d power, you're going to get s to this long exponent. So that'll be, I'm sorry, r to the d power. R to the d power, raise r to this long exponent. So that'll be r to the k to the x times r to the phi of n to the y. And this is now shoot. Hang on. I'm trying to get a contradiction to the fact that s is a primitive root. So I'm going to show you that s to a lower power than phi of n is actually equal to the identity mod n. And that is going to be shoot. I'm sorry. Yes, I didn't need to put these last couple of lines in there. I'm sorry. So let's take s to the exponent of phi of n over d. So now from the definition of s here, or I mean the description of s as a power of r, this is going to be r to the k raised to this exponent phi of n over d. But this d is a divisor of k. So I'm going to write it as, I used the fact that d is a divisor of phi of n already, but it's also a divisor of k. So I'm going to write it as r to the phi of n times this integer k over d. But r to the phi of n is already congruent to 1. So I've just raised 1 to an exponent, and I'm going to get 1, of course. So now I have an exponent that's going to be strictly less than phi of n. That exponent on the s is giving me a 1. Well, that violates the definition of s being a primitive root. So this is a contradiction, contradicts the fact that s is a primitive root unless d is equal to 1. Okay, sorry about the delay in there. So if you want to get a primitive root, another primitive root, the only way to do it is to take r and raise it to an exponent, which is co-prime to phi of n. And the example that I had with n equals 7, that really is very limiting. There's so few classes that are invertible mod 6. All right, so that says that this index, so this is exactly the thing that I called k in this problem, this index of s mod r that is invertible modulo phi of n. And so when I claim that this number is congruent to this number, that's the same as saying that that the third number over here, oops, sorry, you can't see what I'm pointing to. This third number over here is actually the product of these other two. It's the index mod s, the base s of b times the index base r of s. So this is what I'll show now. Now that I know that this one is invertible, then this statement that I want to prove is equivalent to this statement that I'm about to prove. All right, and this is the thing that I called k here a second ago. And if I just give a shorthand for this number as well, I guess I've got a k, so let's call this one L. Then saying that the index mod s, the index base s of b is this number L, that means that b can be written as s to the L power. But now when I combine that with the definition of K, this one said that S was expressible as R to the K power. So if you combine these two statements, I should say these are all congruence is mod N. These two put together would say that B is congruent to R to the K to the L, which is R to the KL. So now I have found an exponent on R that gives me a B. That's what this number here is. And I've just, by definition, and now that I've just shown that that number is actually going to be K times L. So take this exponent and take that exponent, and when you multiply them together, they become an exponent which does the magic that I need it to do. So you have a way of changing a base. If you have more than one primitive root in mind, you can change your logarithm base, excuse me, your index base R to an index base S. Now, let me show you some things that we can do with these indices. Well, first of all, they do allow us to compute powers very rapidly. We can solve questions that have power questions in them very easily as well. So let's just take something like one of the ones that you had on the exam, but I'll use smaller numbers so that this is a little easier to do. Suppose that I ask you to solve the question of, can you write 2 to the x power, and it's a little low here. How about if I ask you to solve 3 to the x power is congruent to 2 mod 7. So we have a congruential equation to solve. It's got exponentiation in it, and there's an unknown in there. Well, I can, when the unknown is in the exponent, I can solve it this way. I can take the indices mod 5 of both sides, just as you would take a logarithm in a high school course. So this congruence will be true if and only if x times the index base, I'll use 5 as my primitive root still, of 3 has to be congruent to the index base 5 of 2. And remember, this is not mod 7, it's mod phi of 7. Well, that's easy enough to do once the table has been created. Where's my table of indices? There it is. Oopsie. Sorry, my papers are flying around. So let's see, what's the index of 3? We got a 3 when we took the exponent on the 5 to be a 5. So this one is x times 5. And the index of 2, where's the 2? 2 is right here, so that one's a 4. This one's not invertible, but this one is, which means that there will be a solution. And my solution is that x is congruent to 5 inverse times 4 modulo 6. Well, mod 6, the inverse of 5 is 5, and 5 times 4 is 20, which mod 6, that's congruent to 2. Mod 6. So it seems to me that the solution to my problem is x equals 2, or any number that's 2 more than a multiple of 6. So let's check. Is it really true that 3 squared is congruent to 2 mod 7? And the answer obviously is yes. 3 squared is 9, which is congruent to 2. In the same way, I could solve an exponential kind of equation with an unknown in it, where the unknown is the base. So suppose I ask you to solve this equation. Let's try x to the, let's try x squared is congruent to 2 mod 7. So the method of solution is the same. You take the logarithm or the index mod 5, index base 5 of both sides. So you'll need 2 times the index of x has to be congruent to the index of 2. And that's, as usual, done modulo 6. So what's the index of 2? Let's see, 2 shows up under a 4. So this side is a 4. So you need to solve 2 times, can I just call this y for a moment? 2 times y has to be congruent to 4 modulo 6. Now in this case, this number is not invertible, so I have to be a little careful discussing the solutions. You don't even know that solutions exist in general, unless you know that the GCD of these 2 numbers divides that number. Well, it does. The GCD of 2 and 6 is equal to 6. Is equal to 2. So I can cut everything through by a factor of 2, and I get this congruence. So what that tells you is that there do exist solutions in this case, but there will exist multiple solutions. Namely, you will have that y is congruent to either 2 or to 5 modulo 6. Those seem like both equally good answers. And so let's read out who has an index of 2 or 5. That means I need to take y to be either 5 squared or 5 to the 5th. When I take 5 squared, the answer is 4. And 5 to the 5th, the answer is 3. So apparently there are 2 numbers whose squares are congruent to 2 modulo 7. Namely, 4 squared is 16, which is congruent to 2, and 3 squared is 9, which is congruent to 2 as well. Cool? You impressed? Okay, now this example is actually very telling. There's a definition that goes in this, and that is that you discover at some point that, well, first of all, as we saw here, not every one of the problems of this sort will have a solution. You can only expect to solve a problem like this if, when you write it in terms of the indices, this coefficient here is invertible, or if it fails to be invertible, the GCD of that number with the phi of n has to divide the index on that side. So there's the possibility that there is no solution. And secondarily, if there is a solution, there may be multiple solutions. And that all of that begins whenever you have something of the simple sort where you're asking for a power of an unknown to be congruent to something. The very lowest case of interest, of course, is when the exponent is 2. So here is the terminology, classic terminology. We say that a number A is a quadratic residue mod n if the equation x squared is congruent to A has a solution. You could have said, and I don't know why the history didn't follow through here, I don't know why they don't just say the word square. That would have been so many fewer letters. But we're saying that a number is a square mod n if it is the square of something, mod n. And it's clear from this one example that we did that some numbers will be squares, and when they're a square of something, they're going to be a square of more than one thing, potentially, but not everything is a square. So, a couple of observations to make here. The first is that this pen is dying as well. So, if x is a quadratic residue, if A is a quadratic residue, mod n, nope, that's silver, you can't see that either. Oh, got it. Then actually this number A will have 2 square roots. Then x is congruent to some number B is a solution. So if, how should I say this? If x squared is congruent to, if b squared is congruent to a, then the only other solution would be to take the negative of b and square that. And that's the, if this, then this is true, is the only other solution. And that's clear when you look at how I went and solved this one. If you are trying to solve a quadratic equation, that coefficient is a 2, then I had to divide everything through by a 2, and that gave me a modulus that was exactly half as big as phi of n. So the two possible solutions are whatever I wrote the first time, or that number plus this one right here, what you just added, that's phi of n over 2. Now, mind you, whenever you're choosing n to be one of these numbers for which there is a primitive root, phi of n is an even number, so this part will always be even, but that will come into play when you're trying to solve that quadratic equation. You had an exponent of 2, which has become a coefficient of 2 after we take logs, after we take these indices. So there will always be two solutions, and they will differ in the exponent by this quantity. Of course, we know that that means that you're only going to find one other solution, and that other solution is just the negative of the one that you found in the first place. The other thing that's relevant about the example that we did is the following observation that says that a number a is a quadratic residue if and only if the index modulo your primitive root is even. And that's the situation we ran into in this last example. Right here, this was the index of the number I was trying to find the square root of. That index was 4, which was even, so I could divide both sides by 2. If this had been odd, then there would have been no solution. So we've identified the quadratic residues. They are exactly all of the powers that you get, sorry, all of the numbers that you get that have an even exponent. Well, you know what? That exponent is either even or odd. Those are the only two possibilities. And one thing I know about evens and odds is that the sum of two odd numbers is even. So you're immediately left with the following great theorem. If you have two non-squares, then you multiply them together and you'll discover that that is a square. The product of two squares is obviously a square. The product of a square and a non-square is easily shown to be not a square either. But when you multiply two non-squares together, assuming you have a primitive root, mind you, then the product of the two non-squares is automatically a square. And that's just because if they're both not squares, then their indices are both odd, and the sum of two odd numbers is even, which makes their product into a quadratic residue. Okay, I am obviously over, so I will stop, but I will alert you to the fact that this business of identifying which numbers are squares and which ones are not has got a long history, and one of the results that I want to work with you guys in the last days of the semester is this famous theorem by Gauss called quadratic reciprocity, and it helps us identify exactly which elements are squares, even if you can't figure out a primitive root. It's a lovely result, and it's non-trivial even to state it, but it's got a very elegant kind of a description. All right, with this as my final slide, I think that's a good place to stop. Comments or questions? All righty, guys. Have fun learning a little bit about the index calculations, and I will just pick up on this theme on Friday.
Are you gonna have office hours?
Oh yes, I'm moving to office hours now, but I got to shut this meeting down. The classes get recorded, the office hours do not. So I'll end this one and start the next one.